I'm going to go over the chapter 15, 16 exam review. That's for aqueous solutions and concentrations, calculating molarities. And this is for my advanced chemistry class, 6th period. Alright, number 1. You definitely should know the definition of molarity, which is big M. The definition of molarity equals moles of solute, that's a substance being dissolved, per liters of solution. So the answer is C. What's wrong about these is no solvents, and it's U would be micromoles. And now you could also define that as a millimole of solute per milliliter of solution. So those are two good definitions. Mole per liter of solute per solution, or millimole per milliliter of solution, which we'll use later on. The answer is C. Which of the following operations yields your number of moles of solute? Okay, so I'm going to use it just like it's dimensional analysis. Moles of solute. That's what I want. Okay. Now you have several things here going on. You have volume of solution. Using this as a conversion factor, you want to convert moles of your solute to liters of your solution, and I want to be able to have liters canceled out, and then I would end up with moles on top. To do that, you would have to multiply by liters of solution, and liters of solution is the volume, and moles per liter would be the molarity. So volume times molarity always gives you the number of moles. If you started off with liters, you would get moles. If you started off with milliliters, then you would get millimoles. So they just flipped the order here. I'm looking for C, molarity, volume times molarity of solution. Okay. If you tried any of the rest, like this one has moles divided by volume, so that would be a mole per liter. If you divided it by volume, you'd get liters squared on the bottom, so that wouldn't work out. Okay, a dilute solvent, the word dilute means this. It means you don't have, your molarity is very low, so you don't have a lot of moles. But as far as the bottom, liters of solution, to make that number small, it means you also have a lot of liters of solution. So you want not a large amount of solute, okay? You want a small amount of solute, not in a small amount of solvent. You want D, a small amount of solute in a large amount of solvent. C would kind of be correct, but D is more correct because it also has a small amount of solute, so I'm looking for D. What does not change in a solution when you dilute it by adding a solvent? Okay, so if I have a solution with particles in it, and I add more solution to it, the number of particles doesn't change. So what doesn't change would be your solvent is changing, your solution's changing. So the only thing that's right is C. The number of moles of solute is still the same. Okay. A tenfold dilution of a sample can be obtained by taking, well, to make it tenfold, you want 1 part of your solute, and the bottom, to make a solution equals your solute plus your solvent. So you'd have to take that 1 part solute and add it to 9 more parts of solvent. So at the end, all you have to add to it is 9 parts of your solvent, because you still have that 1 part solute, and then your ratio would be 1 out of 10. So it would really be A. I wouldn't really ask you a question like that. Alright. Potassium ions, they're all 0.10 molar, and this actually goes back to the lab we did on electrolytes. I'm going to look at the formula for each of these. So I got +1, -3, so I have 3 to 1. So the formula for potassium solvent phosphate is K3PO4. Then I have potassium, K, hydrogen, and carbonate. That only has 1 K, this one has 3. Potassium hypochlorite, do this over here, KClO, that only has 1 potassium in it. Potassium iodide only has 1 K in it, it's +1, -1. +1, -2, so you got 2 potassiums. So the one that has the highest concentration of potassium is going to be the one that has 3 potassiums in the formula. The concentration of potassium in it would be that for every 1 mole of K3PO4, you're going to get 3 moles of K as a ratio. So the ratio, if I just looked at potassium, I'd say it's 0.3 molar potassium ion. And again, from that lab, K3PO4, when I dissolve that in water, I get 3 Ks out of it for every 1 phosphate. So that has a tripling effect if you're just looking at the Ks. Okay. Alright, now we get into most of the tests that we're going to do is going to be dimensional analysis like this. So 7, it asks me for the concentration. When it asks me for the concentration, I'm going to define the concentration as moles per liter of solution. It's always useful, just like gas laws, to create a list of variables that we have. We have 9.3 grams of NaCl. Okay, they give you the molar mass of NaCl. We have 350 milliliters of solution. Okay, so what I need to do to get what I want is to take my 350 milliliters of solution and convert it to liters. So 1,000 milliliters to 1 liter would be 0.350. So I know the bottom, 0.350. And I'm going to plug it into what I'm defining as the concentration. Now, I have, starting with 9.3 grams of sodium chloride, I need to find moles of sodium chloride. So we'll use the molar mass, grams per mole, which is given to us 58.44, but everyone should always know how to do a molar mass from the periodic table. You would add 1 sodium and 1 chlorine. 23 plus 35.5 is 58, roughly speaking. Now, 9.3 divided by 58.44. So I got 0.16. I plug that into my molarity, and then all I need to do to solve it is divide it. 2 sig figs, the answer would be 0.45 molar. C. I mentioned a different way of defining molarity. If I define molarity as millimoles per milliliter of solution, sometimes, especially later on, I like to use millimoles a lot. Well, you already have the milliliters, so you don't have to do this operation. You can just plug in 350. And then instead of looking for moles of NaOH, you could look for millimoles. And then you would go from a mole to a millimole. You'd multiply it by 1,000. So you get 0.16 times 1,000. You get 160 millimoles. And if you divide 160 by 350, it's the same ratio. You still get 0.45 molar. So you get the same answer. you know, once you start working with millimoles, you might decide that you like doing it all the time. Um, Either way, one of these involved a conversion from 1,000 to 1. It's just where you did it. But the ratio ends up the same. This would be times 1,000 times 1,000, which cancels out. Okay. Go to number 8. Um, Again, they're asking you for concentration, so they're asking you for molarity. So the first thing you want to do is define your molarity. Okay. I can define it as moles per liter. If at this point you wanted to define it as millimoles per milliliter, that'll work too. You need to take your 35, what are you given? You're given 35.5 milliliters of solution. You're given 52.5 grams of sucrose, C12H22O11 sucrose. And you're looking for your molarity, moles per liter, question mark. Okay, so I define molarity, and now I'm going to start with the 35.5. What I'm after is I want the moles and I want the liters. So milliliters is going to get you the liters. So milliliter to liter, 1,000 to 1, just like the last problem, 0.350. I plug that in, and now I'm looking for my moles of sucrose. Okay, so I got 52.5 grams of C12H22O11. And then you want to go from gram to a mole. We're given the molar mass 342.3 to 1. So 52.5 divided by 342.3, 0.153. Divide that by 0.350. And my answer is 0.438. I just think I missed something there. 52.5 divided by 342.3, 0.153 divided by 0.350. I think I got a typo on here. The answer, this shouldn't have a 1 in front of it. And yeah, I'm getting 0.438. So that's not really close, but I'll just say, let's call it B. I don't see an answer on there, so there's definitely a typo on it. Oh, let's see what I did. 355. $4.22. All right. There was a problem with one of the answers, but the answer you should have got is 0.422 moles, big M, which is the same as saying 0.422 moles per liter. Okay. How many grams of solution are there in 550 milliliters? Number 9. Question mark. I want to know how many grams there are. I'm given 550 milliliters. And I'm given 1.9 mole as a molarity. Whenever you're given a molarity, take the big M and define it as moles per liter. So this is 1.90 moles per 1 liter. Okay, so we're going to find out how many grams of NaCl there are. I don't want to start with the conversion factor with the molarity. I want to start with the volume. If you look at your mole map, starting with 550 milliliters, I can go from a milliliter to a liter, 1,000 to 1, so I can use liters to moles. Liter to a mole, that's the molarity. That's your 1.90 per 1 used as a conversion factor. And then the last step, mole per gram, which is the molar mass, salt 58.44 to 1 of NaCl. So get 550 divided by 1,000 times 1.9 times 58.44, and you got 61.1 A. Okay, 10. Again, you want to know moles of HCl. You're given a volume of 0.70 liters solution, and you're given a molarity, so I got 0.33. I'm going to define big M. As always, I want to define that as moles per liter. Okay, I want to find moles of HCl on the right. I start with 0.70 liters. So you simply want to convert from a liter to a mole, and the conversion is there's 0.33 for every one. So the answer is 0.33 times 0.7, 0.23 moles of HCl. A solution contains 1.90 moles of sodium hydroxide. Its concentration is 0.555 moles of NaOH. That's per 1 liter. I always define M as moles per liter, so it'll be 0.555 to 1. Okay. What is its volume? So liters equals question mark. Okay, so I want to go to liters. This is just straight dimensional analysis. So 1.90 moles of NaOH, a mole to a liter. That's the molarity, which is the 0.555's on bottom, the one's on top. So I'm going to take 1.9 dividing by 0.555, and the answer I get is 3.42. Okay. Now the process I'm using is dimensional analysis. I don't really get into using equations. I mean, as an equation, there's people who'll be like molarity equals moles per liter, and they'll set up formulas where they can say like, okay, your molarity 0.555 equals, we're trying to solve for the liters, and the moles is 1.9. And they'll say, oh, solve that algebraically. Well, that's the same thing I'm doing here with dimensional analysis. Okay. This is how, honestly, chemistry in the 1950s and the 1960s and 70s, this is proportions. Starting around the 1980s, dimensional analysis is what took over. And in most chemistry, you want to use dimensional analysis to solve your problems. 12. I need the concentration of sodium iodide ions. Okay. Now, it starts you off with a concentration. So I'm starting off with 0.193 moles, and I'm just going to label it. Barium iodide is 1:2 ratio, so it's Ba I2 per 1 liter. Now, what I'm asking you is for the moles of just iodine per 1 liter. Okay, if you put barium iodide in water, and again, this was off the electrolytes lab, it'll dissociate into 1 mole of barium, but for every 1 mole of barium iodide, you get 2 moles of iodine being released. So there's a ratio that we can use moles of barium iodide to moles of just iodide. There's 2 for every 1, so all you want to do is double 0.193. And your answer is 0.386. And that's B. And if you're using dimensional analysis and labeling all your units, it's fairly easy to see. Okay. If you're looking at proportions, sometimes you'll miss a problem like that. Okay, last page. Make sure everything's lined up okay. Similar problem. I have aluminum bromide. If I dissociate that and put that into water, into an aqueous solution, it dissolves into aluminum for every 3 bromides. Okay. So I'm going to put dimensional analysis to this. I start off with knowing that there's 0.500 liters, and I know the molarity is 0.1 molar AlBl3 for every 1 liter. And what it wants to know is your number of moles of just bromide. So dimensional analysis, you'll see how well it works. I'm looking for moles of bromide. Question mark. I start with my 0.500 liters. Again, it's really good to look at your mole map to see where you're going. You're going from liters to moles. Now this is aluminum bromide, AlBl3, and putting labels on it becomes a real essential trait factor that you want to do. So if I make sure that I label this, I know that this is AlBr3. Well, I just want to know moles of bromide. And when it dissolves in water, you'll see that 1 mole of aluminum bromide yields 3 moles of bromide. I wouldn't put the 3 down there in a subscript because these are 3 negative ions. They wouldn't stay together. This means they're separate. They break up. And that's your answer. So I got 0.5 times 0.1 times 3. 0.15 moles of bromide. And you can see how well dimensional analysis lays out a problem like that. Okay. There are what concentrations of Fe and iodine by dissolving 0.2 moles of FeI3 in water and then diluting to 725. Alright. I want to find concentration, so I want to find the molarity of Fe to the number of liters of solution. So I got 725 milliliters. I need to convert that to liters, so I'm going to go from milliliters on the bottom to liters on top, divide by 1,000. I got 0.750. Okay. This will equal the molarity of the Fe. Okay. The other side of the problem is they also want iodine. So it's the moles of iodine per 0.750 liters. And then let's get the top. Okay. Starting off with 0.2 moles of FeI3. Well, that's going to give you 1 mole of Fe, so the 0.2 goes right in there. Okay, because it's a 1-to-1 ratio. And for iodine, for every mole of FeI3, you get 3 moles of iodine. So you get 0.6 moles of iodine. So this one will be 0.60. So for the first one, 0.2 divided by 0.750, that's 0.267 of Fe.